Hello everyone, this video discusses thermochemical stoichiometry, which sounds hard, but it's actually the stoichiometry that you've been dealing with all year. And basically we're going to use the previous knowledge of our mole to mole, so our mole ratio, and mole to gram conversions. So it's going to be the same idea, only now we're including enthalpy, okay? So we're going to take the enthalpy of a reaction and use that in what we call the molar heat ratio, which I discussed in our last video. Okay, so basic idea, you are always going to look out for what's given to you and what you're trying to find. Okay, so in this case, it's asking us to calculate the amount of energy. Okay, we know that energy is measured in joules or kilojoules. In this case, it's kilojoules. Involved when 3.5 moles of aluminum oxide is decomposed. So what they're giving us is 3.75 moles of aluminum oxide. I'm looking for energy. In this case, it's also enthalpy. Remember, they're kind of interchangeable. The equation I'm going to use is the balanced chemical equation here. As you can see, we are putting in 2 moles of aluminum oxide plus 3,352 kilojoules of energy. So these are my reactants. The fact that heat or energy is my reactant shows that this is an endothermic reaction. And we are producing 4 moles of aluminum and 3 moles of oxygen gas. Okay, so we're going to use this information, we're going to use the mole ratio to determine, okay, how much energy is produced if I'm putting in 3.75 moles of aluminum oxide into this reaction. Okay, so I'm going to start with my given. And I'm going to set up my train tracks. Remember, we want to keep up with the diagonal rule. So if I'm in moles of aluminum oxide up here, I'm going to put moles of aluminum oxide down here. And what I'm trying to determine is the amount of energy, so the amount of kilojoules. Okay, so now what you're going to do is you're going to look at your balanced chemical equation. This is where you get all of your information. Okay, so per the equation, it says that 2 moles of aluminum oxide are going to make 3,352 kilojoules of energy. So this I got from the reaction itself. This is what is given to me. So you take your given, use the information provided, and that will help you solve for kilojoules. Okay, moles of aluminum oxide are going to cancel out. So this is gone and this is gone, and you are left with kilojoules. Okay. Okay, so this top is the example I just did. It's just a more clean view. Those of you who like to use the guess method, our given was 3.75 moles, unknown as energy. The equation that I used is from your balanced chemical equation. So I looked at the ratio, starting with our given mole ratio per amount of energy produced, and this is our answer here. Next one is the same idea. Here they're asking us to calculate the moles of ethane, which is this substance here, C2H6. And my given is 100 kilojoules of energy. So I start with my given. I'm looking for moles of ethane. And per my balanced chemical equation, they're saying that 3,120 kilojoules of energy are used to produce 2 moles of ethane. So we start with our given. Per the diagonal rule, remember, whatever you start with, you want the same amount, or the same unit rather, on the bottom. This came from my balanced chemical equation. I'm using it to go from kilojoules to moles. Okay, so again, we're starting with our given and then looking at our balanced chemical equation to determine how many moles of a substance requires a certain amount of energy. Now, if you notice, my enthalpy or energy here is negative 3,000. Okay, so you're probably wondering, okay, why didn't she use 3,000? Or excuse me, negative 3,000. Well, that's because we're solving for moles, and you really can't get a negative value for moles. So remember, heat lost is equal to heat gained. So essentially it is the same number. So it's okay if I made it positive here. Okay, so we're going to go on to the next example. Okay, so this is the last example on this page. Here I'm given 322 kilojoules of energy. I have my reaction. This is the combustion of ethane. It's actually the same as the previous reaction, but now we're looking for mass. Okay, so you're going to have to use your conversion of going from moles to grams. Which, remember, if anytime you're going from moles to grams, you're going to need the molar mass of that substance. In this case, it's ethane. Okay, so you're going to take the molar mass of carbon, which is 12.01. There's 2 carbons, so that's 24.02 grams per mole. Hydrogen is 1.008. There's 6 of those, so that's going to equal 6.048. And now to get the total molar mass, we have to add these up. And that's going to be 30.068 grams per mole. So this is the molar mass of ethane. I'm going to need it in a moment. Okay, so we're going to get the conversion started. My given is 322 kilojoules of heat. Set up your train track. The equation says that there are 3,120 kilojoules used when 2 moles of ethane is involved. And then to go from moles to grams, I need the molar mass, which we previously calculated. So that's 30.068 grams per 1 mole. Okay, so notice my conversions here. Okay, I started with my given was kilojoules. So per the diagonal rule, I have kilojoules on the bottom. These now canceled. Okay, per the equation, here's my equation. All right, 2 moles of ethane went into it. This is how much energy was produced. So this is not random. This came from the balanced chemical reaction. All right, and that's where I got this 2 moles of ethane. Okay, and then to go from moles to grams, now these moles got to cancel out. Okay, and you have to remember that molar mass is grams per mole. So now you're left with grams, which is what you want. Okay, and that is it for this video. Oh, and here's the answer for that last one. Okay, have a good one.